Hey guys, I'm going to go over predicting products of chemical reactions with you real quick. Just as a little cheat, you might want to write this stuff down real quick. Just pause it, write it down. Um, First, we have the way to tell you have a synthesis equation if you only have the reactants is because you only have two elements. Usually, there's a couple of exceptions to that. We'll talk about those. So it starts with two different elements, no compounds. The way to tell you have decomposition is you only have one reactant, okay? Um, so just one single reactant to start with. The way to tell you're starting as a single replacement is you have a compound and an element to start with. If you're starting with a double replacement, you have a compound and a compound. And if it's combustion and you only have the reactants, you're gonna see something with C and H's. So you might see like C2H6 or C3H8. And sometimes you might see something like C2HO2, something like that in your reactants. And then your second reactant is always going to be oxygen. So plus O2, plus O2. And this right away tells you that it's a combustion reaction. And all of that determines how we predict our products. So first I want to go through synthesis equations with you guys, predicting the products of a synthesis reaction. So let's say I start with hydrogen and oxygen, okay? We know that hydrogen and oxygen are both diatomics. So to write hydrogen, we write H2 plus O2, okay? Now, we need to figure out what type of reaction this is. Obviously, it's going to be a synthesis reaction because we have two different elements to start with. So all we're going to do for our product is we know that these are going to synthesize. They're going to be put together. So we have hydrogen with a 1 plus charge. We have oxygen with a 2 minus charge. So that makes this H2O. So two elements became one product, one compound. We do have to balance everything. If you leave anything unbalanced at this point, it's just going to get marked wrong. So always remember to balance your equations. Another example of a synthesis reaction would be magnesium and phosphorus. Well, let me erase so I can kind of go through this with you guys. All right, so we started with magnesium. Magnesium is not diatomic, so when it's alone, it is truly alone. It doesn't get a 2. And phosphorus also not a diatomic, so we start with Mg and P. So we have two different elements. We're going to go through a synthesis reaction and be put together. Now, here's the thing. You are writing a new compound, a new formula. You have to take the charges into account when you're writing a new formula. So every time you write a product, you have to start from scratch and write new formulas. So magnesium has a charge of 2. Phosphorus has a charge of 3 minus. So our product is going to be Mg3P2. And then, of course, I need to balance it, and I'm done. All right, for decomposition reactions, you start with only one reactant. Now, I'm not going to have you guys, I didn't teach all this year. I didn't make you guys remember how this works with carbonates and so on and so forth. I'm just going to show you an example here. You don't even need to write this one down. I just want to make sure you've seen it so you know that it's not always going to break down just into two simple elements. So, for example, strontium carbonate, SrCO3, instead of just breaking down into strontium, Sr, plus CO3, which it can't do because CO3 is actually an ion, what it does is it breaks down into strontium oxide and carbon dioxide. So decomposition isn't always that simple, but on the quiz or test, I'm not going to give you one of these difficult ones. So what you are going to be responsible for is the ones that break down into their elements. So let's say I give you, just get rid of all of this real quick. Sorry. Little bits everywhere. Okay. Let's say I gave you, let me think, potassium, potassium Stop writing. Nitride as our starting point. Okay, so we know potassium nitride is K with a 1 plus charge, nitrogen has a 3 minus charge. So we're going to get K3N. And that's what we start with. That's a truly terrible N. It's not much better. So K3N. So it's going to decompose or break down into pieces. So the ones that usually just break down into the elements are the ones that you're concerned with, a 2-element compound. So what this is going to do is it's going to break down into potassium. Think of Brinkelhoff, okay? Potassium is not a diatomic. It's not part of Brinkelhoff. So it doesn't get a 2 when it's by itself. Brinkelhoff, nitrogen is, so it does get a 2 when it's by itself. So then what we have to do, we're going to have to go ahead and balance that equation, and that's it. It just breaks down into separate elements. So that's a decomposition. Another example here is AlCl3 breaks down into aluminum and chlorine. All right, let's go to double replacement. We'll get to single in a few minutes. It's a little more complicated. So double replacement, here's the key here. What is happening in a double replacement is that the 2 cations switch partners, okay? So cations switch partners. You're not going to have 2 cations together. That's a mistake I saw some people making today. They started putting their cations together. That's not what's happening. Yeah, get this ready to go over with you guys. All right. Get rid of all of this mess. Okay. Now let's scroll down. So what happens here is, first of all, you know you have a double replacement reaction or displacement reaction because you start with a compound and a compound. Okay. So the first thing you need to do is pick out your cations. Aluminum is a cation. That's your metal. It's positively charged. Mercury here is a cation. That's your metal. It's positively charged. What those guys are going to do is they're going to switch places. They're going to switch partners. So aluminum is going to come in here and kick out mercury. So it's going to be with chlorine now. So since aluminum is now with chlorine, we're writing new formulas. Aluminum has a 3 plus charge. Chlorine has a 1 minus. So this is going to be AlCl3. Now the mercury has to go somewhere. So what it does is it comes out here and now it pairs up with bromine. So mercury is a transition metal, but from this formula, we know it's mercury 2. So Hg has a charge of 2. Bromine has a charge of 1 minus. So we're going to get HgBr2. Then all that's left to do is we're going to balance, get rid of this, do my balancing. What you got? You got you got a 3, I think a 2, 2, and a 3. Yeah, that's right. Okay, so those two, the cations switched partners. So anytime you have a compound and a compound, that's what's going to happen. And remember, you're writing whole new formulas, so you have to worry about charges, okay? It's like starting from scratch. Let's talk combustion. Combustion, your products are always going to be carbon dioxide and water. Anytime you start with C's and H's and O's, you've got a combustion reaction, okay? So this one starts with dicarbon octahydride. So C2H8. Oxygen is always going to be reactant. So if you just start with something with C's and H's, you're always going to have oxygen as your other reactant. You don't even have to think about this. You don't have to switch anything or anything like that. Your products are always CO2 and H2O. Okay, so, and then you need to balance it. And that's what happens with a combustion reaction. Always CO2 and H2O when you see these C's, H's, and O's start the equation. If I had instead, let's say we have, just make one up. I'm not even going to balance it because it probably won't balance correctly. Let's say we have C3H2O to start with. Since I started with a compound that just has C's and H's or C's, H's, and O's in it, I know oxygen's going to be my other reactant because I know this is going to be a combustion reaction, and I'm going to have CO2 plus H2O as my products. Okay, I could have C7H12, and I know then I'm also going to have oxygen because I just started with C's and H's, and I'm going to get CO2 plus H2O. All right, now let's talk single replacement. You're going to use something called the activity series. The activity series is actually in your packet. The activity series of just metals is on the back of the Chem Cruncher. Basically, if you look at your activity series, hold on and just let me find mine here real quick so I can show you what I'm talking about. So I gave you this activity series chart or one like it. And basically what happens is if you have a single element, so like in a single react or single replacement, something like lithium, it can replace anything below it. But if you have manganese and your other element is calcium, it cannot replace it because it's not, calcium's not below it. And I'll explain this in a second. And no reaction will occur. There's also a activity series for nonmetals. There aren't very many of them on this, but you'll use that from time to time too. So use that activity series that's in your packet. So a metal can replace a metal that is lower than it on the activity series. A halogen can replace a halogen that is lower than it on the activity series. Oh, and apparently I can't erase this. All right, so I can't erase anything. Let me do this. So if I did AlOH3 plus sodium, what I'm looking at here is I'm going to look at my single element. So I know this is single replacement because I have an element and I have a compound. So sodium is my single element. I need to look first at what sodium is. Is it a cation or an anion? We know sodium is a positive metal, so we know it's a cation. So if it's a cation, it can only replace the cation in the compound. That stands for compound. So which is our cation in the compound, aluminum or hydroxide? We know it's aluminum. So basically sodium is going to come in here and replace aluminum if it can. So that's where we need to look at our activity series. We need to see if sodium, since it's single, is above aluminum. And it is. Since sodium is above aluminum on the activity series, it can replace it. Okay, so what you're going to get here is you're going to get sodium is now with OH. We know Na1 plus, OH1 minus. So we get NaOH plus. So what happens is that the aluminum ends up out here all alone. It is not a diatomic, so it doesn't get a 2 down there. And then all we would have to do is go ahead and put some 3s there to balance it. So if instead, oops, wanted to keep that, so let me, all right, if instead, that line there, we had kind of the opposite is a good way to look at this. If we started with NaOH plus aluminum, looking at this, now we need to look at the aluminum on our activity series. All right, so here's your aluminum on the activity series, and it is not above the sodium, so it cannot replace it. If it cannot replace it, you just write NR for no reaction. You don't need to balance, you don't need to do anything, you need to put that there is no reaction. Okay? If you have something like, I don't know, let's do sodium. Let me look at this real quick. Sodium bromide plus fluorine. Let's take a look. Fluorine is an anion. So we need to look at this angle. It's an anion. An anion can only replace an anion. So look at our compound. Which one's the anion? It's bromine. So now we need to see, can fluorine replace bromine? Is fluorine above bromine on the activity series? It is above bromine on the activity series, so this will react. So what happens here is our F comes in and takes the place of our Br. So Na1 plus F1 minus. So we've got NaF plus. Now bromine's going to come on out here alone, and it's a diatomic, so it's going to get its 2, and I think we're balanced there. All right, that just gives you a good overview. Hopefully that helps, and just let me know if you have more questions. Thanks.